Hello, and welcome to the third unit in the verilog13.1 module. So far what we've done is generally describe how to produce HDL design using a subset of the synthesizable language. We'll get to a more complete version in the next module. I've illustrated this with a simple example, count.v. Now we're going to complete this example going all the way through the design process. We're going to verify that count.v works and then go on to synthesis. So this is the outline of this particular module, submodule. We are going to look at a test fixture for simulating count.v, then the standard class synthesis script, at least how it's used in Synopsys design compiler. Obviously, you need to be able to test or verify that your code works before going on to synthesis. And in this submodule, I'll present to you how to produce the code that allows you to do that verification. Synthesis is a substantial task that actually involves a lot of scripting. And I'm going to go through the class script in detail in the next submodule and explain why everything is there. So these are our overall objectives: how to write the test fixture, what are the major steps in synthesis, and what are the function of the statements and why are they there. And in this class, I'm going to really emphasize that it's important that the designer understand what the synthesis script is doing and why. This is not just so that you can be an effective designer, it's because a lot of your design intent is really captured in the synthesis script, in particular your timing design intent. And if you get those parts wrong because you just ignore it and just assume it's someone else's responsibility to produce that script, then you'll make errors that will prevent the chip from working. These are the references for this particular submodule and this unit. And I again remind you the Sutherland Reference Guide is a very good overall and quite short guide to the Verilog language. And I encourage you to use it and get familiar with it. So this is the module that we'll be verifying and synthesizing. I'm just going to remind you of the major features in this, the Verilog 2001 version of this counter. Again, start in the middle. We have two procedural blocks here. This is the procedural code version. The first procedural block begins with an always at pos edge clock. So that means it is what? It is the output of a register or an array of a vector of flip-flops. The if-else statement becomes a mux at the input to that register. The next procedural block begins with always at star. Again, I'll remind you that this is combinational logic captured in a behavioral form. Always at star means that this is triggered whenever any of the inputs change, and the simulator works that out for you. It recognizes that when value changes, you want to execute this block. At the top, we have our inputs and outputs combined with whatever declarations are needed for those. In, for example, is 4 bits wide, the most significant bit on the left. 0 is an output, and here is to be declared of type reg. Why is that? Because it's assigned procedurally. It does not mean, and it definitely does not mean in this case, that 0 is the output of a register or flip-flop. We then declare our local variables that are not in the I/O list, and that is value, which is a 4-bit wide variable, again a type reg because it's assigned in a procedural block. So now we're going to go on to look at a Verilog 95 test fixture before looking at a test fixture in Verilog 2001. So obviously we need the test fixture in order to exercise the design, basically to stimulate it and also to collect and observe the output waveforms. You can use any code you want in the test fixture that is functional code. It is not highly constrained like the RTL subset, the synthesizable subset of Verilog. So here is a verilog95 test fixture. Note that not all the features here are needed for every version of the simulator. On the whole, except for the first line here, I've put in features that are useful for the model sim simulator we'll be using in our exercises. Again, let's start at the core of the code. We have an initial block, followed by begin and an end. Obviously, the statements are executed sequentially in this block. Initial block means exactly that. It is executed once upon simulator startup. You could have multiple initial blocks in a test fixture, and it can be quite handy to do so. Do you think that the initial block is synthesizable if it was in a logic description module? The answer is no, absolutely not. This would be like having self-destructing hardware. You turn on your chip, all the initial blocks run, then they disappear forever, so they have to blow themselves up. Obviously, that is not how chips are actually used or built, except maybe in certain circumstances. There are actually chips that will disable themselves under certain circumstances. But nonetheless, we're not designing such a thing, and furthermore, this is not how you would design it. Next, we have some files to save waveforms. Again, I'm trying to be general here to cover multiple simulators. These are actually not needed if you're using Model Sim. But you may or may not need these. And these files can specify things such as which waveforms you're going to save, how many levels of the hierarchy you're going to save the waveforms for, and so on. See these statements here. Before I get into those, notice this hash unit down here. Hash 16 means wait 16 units. The units themselves can be defined elsewhere with a dash timescale. And by the way, I have some notes on the next slide talking about things like this. So what the hash 16 means is wait 16 units before continuing execution. Notice there are no waits in these four initial statements here. So when in simulator time do all those variables get set as such? At time 0. So at time 0, clock 100 becomes 0, latch becomes 0, dec becomes 0, and then becomes decimal 2. Notice the terminology here, clock 100. I'm starting to name my clock specifically. I'm anticipating in a real design to have multiple clocks. I tend to call them by their megahertz rate. Clock 100 is a 100 megahertz clock. So at time 0, all these variables are set as such. 16 nanoseconds later, because the time unit is defined as nanoseconds, latch becomes equal to 1. You'll see why this is 16 in a moment. 10 nanoseconds later, latch becomes equal to 0. 10 nanoseconds later, dec becomes equal to 1. Then everything stays the same for an additional 100 nanoseconds when the $finish command is executed. You notice these dollars here, these dollar commands are commands to the Verilog simulator. You need some way to end the Verilog simulator, so you need a $finish to tell it to end. If you don't do this, the simulator will continue running, and you'll need a Control-C out of it. Then we hit the end statement. We've now finished executing our test fixture. Notice this always at statement down here. What this is specifying is the repetition of the clock. It's basically a loop. Always wait 5, invert the clock. Squiggle means invert. So always wait 5, invert the clock means wait 5, invert the clock, wait 5, invert the clock, wait 5, invert the clock, wait 5, invert the clock until the simulation is finished. This is producing the repetitive clock. And notice the clock is starting at 0 up here. Then you need to actually instance the module that you're using. And we'll talk about this more in the Verilog2 notes, but this is introducing the concept. What we're doing here is we're not calling a subroutine. We're building a copy of the module counter in the test fixture, within the test fixture, and we're calling that copy of counter U1. Every instance of a module has to have a unique name. We are building copies of hardware, not calling subroutines. When we build or instantiate a module, we have to describe how it's connected to our signals within the current level hierarchy, that level hierarchy being test fixture here. And that's what the dot parentheses structure is down the bottom there. So the items in parentheses are the variables within the scope of test fixture. The items with the dots after them are the port names in the module counter. So we're connecting clock 100 from the test fixture to clock in the counter, and so on. Just so happens the rest of these I've kept the names the same. That is convenient. They don't have to be the same, and in fact get a little confusing if they're not, if they are. However, there's no harm in doing this. So we've built a copy of the test fixture, and we're describing how the signals within the test fixture are connected to the ports of the module. The advantage of this dot parentheses format is you don't have to maintain the order of the ports. Now that we've built the module, notice we have an output called 0 here. Right, we're connecting the port of the module called 0 to the signal 0 in the test fixture. Thus we have to declare 0 within the scope of the test fixture. It's of type wire. This again is just a simple rule. All signals that are connected to the outputs of modules are of type wire, or occasionally of type trie. We obviously also have to declare the other signals written within this module. Clock 100, latch, and deck. Since these are signed procedurally, that is in a procedural block between a begin and an end, they are of type reg, and here remember this is not, we're not specifying hardware here, it's just the data type we have to use when a variable is assigned within a procedural block. We have our module name, just calling it test fixture with a semicolon here. There's no ports to the test fixture because as far as our current world is concerned, this is the edge of the universe. The known universe is finishing in the test fixture that's testing the hardware instance within it. We need an end module. Notice there's no semicolon end module. And again, I'm being consistent with a variety of simulators here. If we're using model sim, we refer to count.v when we call model sim. In other simulators, you might want to dash include, which just like in other languages does exactly that. It includes a copy of that file within this structure when it's run in the simulator. Next few slides, just put in words some of the things I just talked about. Dash include includes a copy of the file called count.v. The initial block is a procedural block, just like always is a procedural block. That is, the statements between the begin and the end are executed procedurally in sequence. It is executed once on simulation startup, and it's not synthesizable. There's no hardware that just executes once and then stops forever. Hash something means wait 16 units. Here those units are nanoseconds as defined by dash times, and this can be redefined by the dash timescale command. $dump file and $finish, etc. are Verilog commands. Anything with a dollar is a command to the Verilog language. Again, the Sutherland Guide gives you a complete listing of those commands in a concise format. We have to build or instance a copy of whatever we're testing. So we build one instance of the module counter, calling that instance U1. And again, this dot parentheses format means the item in parentheses is the signal within the test fixture, within the current level of hierarchy. And the dot is the name of the port in the module that you're instancing. And remember, we're building copies of the module, not calling subroutines. Just like the initial block is not buildable, not synthesizable, the always blocks without sensitivity lists aren't either. There's no such thing as a piece of hardware that just always runs no matter what the inputs are. Real hardware changes only when the inputs change. And of course, fixed delays are not synthesizable either. In fact, with the large process variations that we talked about in the timing notes, it's very difficult to get a precise delay in actual hardware. And certainly within synthesizable hardware, there is no mechanism to do that. There is such a thing called a vernier circuit, which you can program to a fixed delay, but that is a transistor level full custom circuit, not a standard cell or a designer or something you can design from RTL. So quite simply, the code in the test fixture is describing a waveform in textual format. The always at 5, clock equals not clock, is simply inverting clock every 5 nanoseconds. Starts at 0, so 0, 5 nanoseconds later go to 1, 5 nanoseconds later go to 0, 5 nanoseconds later go to 1, and so on, until we hit the $finish. I actually haven't taken this for 10 clock cycles, just for the reasons of space. So that is defining the clock, starting at whatever we specify here. Then latch, dec, and in are specified. I haven't shown in here. Because in is just constant, there's not much to see. 16 nanoseconds after the start of simulator time, 5, 10, 15, 16 right here, latch goes to 1. I find for beginning designers, it is useful to see signals changing away from the clock edge. However, there's no harm with that just being -15, changing on the clock edge. Remember, signals on the clock edge are essentially just after it. 10 nanoseconds later, latch goes to 0. These delays accumulate. So at time 26, latch goes to 0. Then at time 36, dec goes to 1. They're not shown here. At time 136, we end the simulation with the $finish command. A very useful feature to add to any test fixture is to use code in the test fixture to actually test your whatever you're simulating. It's much more useful to do this than relying on viewing the waveforms in the waveform viewer and hand checking correct functionality. So for example here, in is set to 2, that's loaded in the counter, dec goes high at time 26. How much time should it take with a 10 nanosecond clock for the 0 flag to go high? It should take 20 nanoseconds. So I can put this command in, #20. If 0 is still low, bang 0 means not 0, so 0 is still low. Display with a $display command, error in 0 flag. /n means new line. So now I've got a self-checking test fixture. It will tell me if something is wrong. The big values of this are, first of all, you don't have to go and hand inspect the waveform viewer. Secondly, now that we know the zero flag works, we're going to start adding features to this design, at least in principle. And you might forget to check that the zero flag was working properly. Well, this checks it for you every time you run. So you don't get that problem which we've all experienced in our coding lives of, it used to work, why isn't it working now? I didn't change it. i.e. side effects, side effect bugs. This will detect if this type of coding style, this self-checking feature, will detect if you accidentally insert side effect bugs. And it is very valuable, and I highly encourage you to do this. This is the same test fixture in the Verilog 2001 format. There's only one change here, and that is, in the Verilog 2001 format, you can initialize variables when they're declared. So here we have reg clock 100 equals 0, reg latch equals 0, reg dec equals 0. This saves us initializing the variables in the initial block, saves us typing, which is most of the features in Verilog 2001 are of that nature, and simplifies and shortens the amount of code. Do you think this is synthesizable? No. Again, you cannot initialize variables in actual hardware. You actually have to build hardware to do that, and we'll talk about using reset to initialize signals within the actual hardware in a later module. So, initializing variables is not synthesizable. Don't do this in RTL. So that brings us to the end of this sub-module in this third unit. Some major points to emphasize. A test fixture provides a Verilog specification that allows you to textually describe your input waveforms. And furthermore, to test the output waveforms, you can write code to look for correct behavior. And this is something I very much encourage you to do. For example, this code will always be there every time you run, and you'll detect side effect bugs through this code. I hope this module was useful to you. I now ask you to do the sub-module quiz before proceeding to the next sub-module, and where we'll start talking about synthesis using Design Compiler. Thank you very much.